Okay, so let me start by reviewing what we have talked yesterday. So suppose that we look at the graph with degree profile D, and what we talked about yesterday basically is to compare well connectivity of any graph that have degree profile D or D restricted less than D. Yeah. And we have first saw that the D product graph, okay, is basically the most well connected one in both cut and flow perspective. Any D restricted graph H is less than 2K, and in both cut and flow sense. Okay? That's what we have. So the product graph is the most well-connected one. And a second thing that we saw is that if the graph G is an expander and degree of G is more than the degree of H on every node, then we know that H is actually less than G on every cut up to this 1/3 factor. And this means that if they have the same, if G1 and G2 are both expander and they have the same degree profile, then just by applying this in both directions, then we have that G1 and G2, if this is a phi expander, then G1 and G2 are cut equivalent, and it's a 1/5 cut equivalent there. Also, just by using approximate max flow mean cut theorem, then we would have that there will be G1 and G2 will be kind of flow equivalent to. And if G1 and G2 are phi expander, what should be the factor of the flow equivalence here? What is it?
Log n.
So, actually I forget this. Yeah. Yeah, log square over phi square. Yeah. Okay. So basically, expander with the same degree profile they are basically equivalent from both flow and cut perspective. And the product graph is in this class too because it is an expander. But because the product graph is the most well-connected one, then it's the most well-connected one with respect to both cut and flow, then the whole class of expander will be most well-connected too because they are equivalent. In other words, if you take any D-restricted graph H, then H will be kind of less than any expander in both flow and cut sense. All right. So that is just a review, and this is a picture that you should have in mind. You have a equivalent class here, and this is the biggest one. And what is this equivalent class? It contains both the product graph and an expander. Okay. And yeah, by the way, I just stress again that the fact that when you know that if G is an expander, and if you just need to know that if you just know that the degree of G dominate the degree of H, then you basically dominate H in both flow and cut sense. This is quite a useful intuition. In some sense, like speak in the formal way, in the informal way, like all that matters for expander is to compare degree, and then if the degree dominates another graph, then you know that it is really bigger than in both flow and cuts sense. Okay. The last thing is that suppose that you want to show that some graph is the most well-connected graph. Then what you need to do, like, it's enough for sure to just show that, like, if this G prime you want to show that it is well connected, then if you can say that it is bigger than the product graph, then you're done for sure. But it's enough to show that G prime is bigger than any expander. Yeah. Okay. Question about this review? Okay. So I would like to continue talk about the thing that I didn't finish properly last time. The thing that I said is the right way to think about expander. Yeah, this is subjective, but it's just easier for me, at least. So what we were talking last time, we have that, let's say that you have a graph G, and I think of G as unweighted graph. And I define G prime to be the graph where I subdivide each edge in graph G. Okay. You have U and V. And now I just subdivide each edge and add a node that represent this edge, E. Okay. And now, so I call this set XE to be all of the split nodes, to be the set that contains all of the split node in G prime. So let's consider the clique on the split node. Okay. If I consider this clique, then note that if I scale down everything in this clique by 1 over m, then every node will have degree 1, right? The weighted degree is 1. And basically, what we want to show is that if you can, like the graph G, so I want to say that the graph is an expander if you can, if an unweighted clique on split node E after scaling by 1 over m, which is, so this is, what is this? This is just 1 over m ke. If this thing is embeddable into G prime, then G will be an expander. And this is if and only if. In the more formal way to say this is that I want to show that if G is in the phi expander, then this clique is a uniform clique, can be embedded into G prime with small expansion, with small congestion. And if it is not an expander, then you cannot embed it with maybe this condition. So I add this factor of 1/100 just to be safe. Yeah. Okay. So just again, why this is a bit easier to think about, because every edge in KE have the same weight. It's not like a product graph that we saw before, where each edge have the weight depends on the degree, or like depends on the endpoint. Yeah. Everything here is uniform degree, uniform weight. So before proving this, what does it mean here? So let's look at any one restricted graph, HE. So think of this. If this is one restricted graph HE, and the node set of HE is on the split node. So this is the thing of this as KE, and I have some HE on the same, and this is like on XE, both of them, right? So what do we know about this? We know that HE must be embeddable into KE, right? Why is that? Well, this is like this is just the thing that we have proved before. Yeah. KE have degree profile 1. Oh, sorry. I should say that even if you, this is important, even if you scale this thing down by this, it has degree profile 1 on every node. And HE is one restricted, so it's embeddable. Okay? And so combining these two inequality, this one and this one, what do we have? We then have that HE must be embeddable into G prime. Right? So in words, it means that if you think of HE as a demand, right? And if you want, and it's a demand on edge, like edge have its demand, and it want to exchange some flow, like send some flow to other edge. And it says that as long as this demand is one restricted between edges, then you can send those demand on an expander. So every edge can exchange one unit of flow between any other edge for any kind of demand, as long as an edge want to send one unit of flow in total, then you can indeed exchange that demand. Does it make sense?
What is the KE's degree profile in this?
KE?
Yeah.
The degree profile will be M, right? Because there are M edges and a clique. Like there are M edges, so yeah. So just to KE have M nodes. And if you look at KE as an unweighted graph, then each of these edges have like weight 1. So its degree is going to be M. maybe with some self-loop too. But if I scale it down by 1 over m, then the degree profile of each node in this graph is going to be 1. So basically, this is really the way that I think about expander. It's just a graph where edges are well connected in the sense that any edge can exchange 1 unit of flow to each other. Okay. Again, if you have any demand on edge, and if maybe you want to send this by 1 over 2, this by 1 over 2, yeah, any demand such that the total degree here is at most 1, then you can indeed send that flow, like multi-commodity flow. Okay. All right, so let's prove it. The proof is actually it's good to see how to prove this kind of thing. So I'm gonna prove this lemma now, okay? And let's prove the first direction. If the graph is an expander, I just, what we need to do is to construct the multi-commodity flow that embed this thing into this. Okay. So I will do exactly that. Let's try to construct this concurrent flow with small congestion. And there will be several steps. So let's do it one by one. So this is KE. And there will be XE here, right? And XE prime. And we know that you want to send 1 over m flow between these two edges. So again, I will draw some direction when I construct the flow, but you should really think it's just like a set of parts between these two things, no direction. Okay. And what I'm gonna do is this. So note that this is in KE, and let's look at G prime. How does it look like in G prime? So XE, this is XE. So XE is between is always between some edge, right? So let me write it like this, and this is XE prime. Okay, this is XE. What I'm gonna do first is just, okay. So at the end, this thing should send flow by 1 over m from XE to XE prime. What I'm gonna do, how I'm gonna construct the flow? I send 1 over 2m here and 1 over 2m here. Okay. First, and somehow this I will say that somehow I want to the flow from U should reach U prime, and the flow from V should reach V prime. Somehow I don't specify yet how to do that. Okay, but once I can do that, I will just send this by 1 over 2m. Okay, so I have construct like partial flow. For every demand, I construct the beginning of how the flow look like and how it should end. Okay, and once I have done that, then this flow kind of it induces new demand. What kind of new demand it says? It just said that instead of trying to send from XE to XE prime, I just said that, okay, now you should send to U prime with this much, and V prime should send to, V should send to V prime by this much. Okay. So you should think of now like each of these U and U prime and V prime as a new demand. Okay, so let's try to see what actually is a total demand that you want, that you need to send. So let's see what is the total demand that you need to send from you. Okay. So basically, you have U here, and you have XE. You have XE, and note that XE would like to send it to all edges, right? Each of the demand from XE is like 1 over M. So that basically all of this demand will induce, like in total, this is like a 1. And for each of these, you send half to U. So that will induce like basically 1/2 from XE. Like the demand from that XE induced to you is 1/2. And you do this for every edge incident to U. For every edge that incident to you, here, this guy, let's maybe call it XE2. This node would like to send to every other edge too, and that will induce another 1/2 of the total demand to you. So in total, the demand at U will be what? Degree of U over 2. Okay. Yeah. So that's what we have. Like by constructing this partial flow at the end and at the beginning and at the end of each demand in KE, you get a new demand. But now this new demand is on your original node set, not on the split node anymore, right? This is a new demand on original node, and each node U have total demand of, like total demand that you need to send from U here is this much. Okay.
Are we not overcounting here?
Sorry?
Are we not overcounting here?
Might be, but yeah, it's at most that. Yeah.
Okay.
Yeah. So this new demand is like a degree over 2 restricted demand, where all the demand pair is between original endpoint. So let's call this demand edge, right? And we have shown that this is like this is a product. Like, okay, we have shown that for any demand which is degree restricted, you can send flow. You can embed it into your graph G. So this is now I invoke the thing that we proved yesterday. Just the fact that any restricted demand you can embed into an expander with small congestion, right? And obviously G can be embedded into G prime because yeah, like you have node UV how would you want to embed demand between this edge into G prime? Well, just go through the same path, right? Just go through this edge. Nothing really happened. Like it's a trivial way to send the flow to embed this G into G prime. So combining these two inequality, you have that indeed H can be embedded into G prime with small congestion. So what do we have? We have that the new demand that we have that is induced before the excess. You can satisfy those demand with some flow, call it F2, with small congestion. So maybe I write it like this. F2 is here. And forget to write. This is. So what is left to do? Well, now we argue from the beginning that we construct partial flow at the beginning and at the end that induces the new demand. And now we know how to satisfy this new demand. So we just need to concatenate the flow. Right? So you have the beginning and use F2 to go to the from U to U prime thing, and then finish your flow at the end. Now, so that is, we have to construct the flow that embeds this guy into G prime successfully. What is a congestion? So let's say that the congestion of F2 is Q2. What is the congestion on this, on the for the whole flow that we look at? So we need to be careful a bit. It's not just Q2, right? Why is that?
Because we are concatenating.
Yeah, we concatenate the path, and maybe the path can overlap. Like the first part that we construct and the F2 thing, they can overlap. So like this, this is a path for S2, F for F2, and this thing, it doesn't really care if it overlaps with the thing that we have construct in the beginning or at the end. So that's why you just need to take care of the congestion in the beginning and at the end, and it was 1/1/2, right? Because the way we have shown here is 1/2. Right, but yeah, it's small anyway. Like 1/2 is small. Okay, so that is how we embed the clique. Sorry, I always forget this thing. Yeah, we embed the clique into G prime. Okay, and another way, let's prove the other direction, which is if G is not an expander, then you cannot really embed a clique. This is going to be easier, actually. So the way to go is just that, well, it's kind of obvious how the proof should go. Even if it is not expander, by definition, it means that the X is a Schwarzschild, So you draw a sparse cut, S here. Let's say S is on the smaller side. And it's sparse. Like this thing, in total, it's almost 5 volume. Okay. So let's try to look at, and now let me define E1. And intuitively, we're gonna just see that basically there are like a lot of edges here. So let me call it E1 here. E1 is just edges inside S. Okay. I can even define to be edges, all edges incident to S, but yeah, that should be fine too. Just edges inside S. So that's E1. And E2 is everything outside. And note that the size of E1 is basically close to its volume, to volume of S. Why? Well, because yeah, this thing is kind of small anyway compared to the volume here, right? It's a small fraction. So E1 is basically almost the whole volume of S anyway. Yeah. So E1 is big. It's like as big as volume of S. And now, if we look at the graph KE now, and look at the set correspond to E1. This is not note that the node in KE correspond to H, right? So I look at the set E1 here and the set E2 here. The point is just that this cut should be too sparse to satisfy demand between E1 and E2. Why? Because if you take any pair of demand here, you know that the flow, if you want to embed this edge into the graph G, this must go past the cut, right? So let's see. So all you need to check if it's just that what's the total demand from E1 into E2. So what is that? What's the total demand from E1 to E2?
E1 into E2 by n square.
Say it again.
Mod E1 into mod E2 by n square.
Mod E1. So I think E1, E2, and so this should be here, and then and this should be over M. Yeah. Just not M squared, because each edge in here has weight 1 over M, right?
But we are only counting number of edges, right?
We are counting number of edges is E1 times E2, but the total like weight of edges between E1 and E2 is this thing over M. But E2 is on the bigger side, so this is like basically E1. Right. Yeah, so this is like E1. So It means that you have total demand that you need to send from E1, which is around, total demand itself is of size around E1. But there is a cut here, which is 5 sparse. And the total capacity here is around 5 E1. Right? Note that E1 and volume are kind of the same. So that's why the cut size here is around 5 E1. So no matter what, you will like to send this much flow through this cut, you must pay 1/phi congestion. And I ignore a lot of constants, so I just put 100 here. Yeah. Okay, so that's the proof question. All right. So, yeah, the proof is actually not too hard, at least for flow. And but actually, you can this statement. You can talk about cut as well, like replace this by cut. But you can try to prove it. It will be true, and you can even prove it with a tighter bound, like you don't lose log n basically. However, if you I don't actually know the way to get a nice and easy proof, because instead of trying to just show that, for example, if this is a flow here, all you need to do is just what we did. Just show that, okay, construct the flow and embed, and you're done. But that is, you just need to show one single flow and you're done. But to show that this is true for cut, you need to kind of argue that this is true for all cut. And it's harder to argue, at least I don't see like the not tedious proof for this. So this is just an example why sometimes you know that cut and flow are kind of equivalent up to log n factor, but sometimes it's just easier to think about flow. Yeah. But yeah, this is true for cut too. If you are careful.
In the previous proof, we showed that 1/5 congestion will be at least needed.
1/5?
Congestion is at least needed. That is what we have shown in the previous proof. If G is not at 5 expanded.
I don't catch. Sorry, my listening.
So in the previous proof, we have shown that 1/5 congestion is needed if G is not a 5 expanded.
What do you mean by 1/5?
1/5.
Oh, okay. Yes, 1/5 is.
Congestion is needed.
Uh-huh.
So why can't it be like 2/5 or 100/5, and that is also acceptable, right?
100. Oh, yeah. Well, I don't really I'm not very careful about the constant here at all.
Something like phi is asymptotically much bigger than log n, and it's not possible. Or something like that.
Sorry, I still don't get the point of the question.
You're trying to say that the expanders are the exact set of graphs which are in which this edge-to-edge flow can be routed.
Yeah.
So up to some log n factor in phi, we are proving that.
Up to log n factor, phi.
In Lemma 7.1 part 2,
yeah.
so if G is not a pi expander, then the demand graph 1 by m or ke, so it can't be embedded into 1 over 100 pi.
Yeah.
Can it be embedded by 100 over 5?
It shouldn't. You should lose a log factor. Yeah.
We should do so.
Yeah.
We just proved that we need 1 by 1 over 5 congestion, right?
One sec. Actually, so let me think. Let me think. It might be like, okay. There might be some expander where you don't lose a log-n factor. For example, if G prime itself is a complete graph, like G prime itself is 1 over m ke, then you don't lose any log-n factor. But there will be some expander where you will lose log-n factor. Yeah. And actually, this is something that you will see in the homework. Yeah.
So in that case, you are telling G is not a pi expander, but G prime can be a expander.
No. G and G prime will be expander, like G and the conductance of G and G prime will be almost the same. Yeah. Like within constant factor. Am I addressing your question properly?
Yeah.
Okay. All right. I think is there actually any question about the thing in class this week that you would like to discuss? Otherwise, I think I will talk more about an open problem that I listed. Project. Okay, my computer is. Do you hear the noise, by the way? Oh no. So actually, is there actually any question, any problem here that you want me to talk more about it? I can just talk about that specifically too. Otherwise, I will just go through it one by one. By the way, this is now online in Canvas, so you can look at it too. So I will just then, maybe I will talk about this one then, right? I don't know how to. Okay. So in this problem, you have hypergraph and you want to know a global mean cut. So let me state the problem. Do you guys know hypergraph actually? I will just state it so that
You mentioned this problem last time.
sorry?
I mean, you explained the problem last time.
Oh, I see. You're right. Yeah, you're right. Then for this thing, for these two things, it seems it's better if I have talk about cut matching game in class first before explaining. So maybe I just talk about this problem, multi-cut. This is very basic question. It is very kind of, yeah, let me just explain the problem and tell you what we want to show. So the problem is just, here you have like S1, T1, S2, T2. Okay. And somehow you would like to remove edges, the minimum number of edges, so that you cut all of the pairs. So you have find phi E star or E minus such that the graph, after you minus this, then for all I, S I is not connect to Ti for all I. And actually this is think of undirected graph actually. It's no direction. So very basic question. So it turns out that the fastest algorithm, let's say that even k is constant. So if k is 1, this is just mean cut problem, minimum cut problem. If k is large, this is NP hard, like we don't expect polynomial time. But if k is constant, then one can do something faster, like then like it's still in polynomial time, but the running time is something like, right now it's mn times f of k. So it's FPT algorithm. It depends exponentially, like it's maybe something like 2 to the k or something worse, I'm not sure. But the point is that the fastest algorithm now is mn when k is a constant. This is a very, very basic question. So one should have fast algorithm. It should be faster than mn. Maybe, can it be the case that, let's say, is it possible to solve this problem in f of like to call max flow? Let's say, can you call f of k calls to max flow or mean cut? Because if you can do that, then right now the fastest max flow algorithm is very fast actually. The fastest max flow algorithm is, so if you can do this, it would imply something like m plus this time f of k, much faster. So that is just one question. Yeah. And there are more questions. So there is this problem which is about, it's called restricted shortest path. So think like this. In shortest path problem, it's clear what is the problem. So you have weight on every edge, and you want to compute the shortest path. But now, imagine that each edge has 2 parameters. So each edge, let's say you have a budget and you have the weight. Okay. These 2 parameters are unrelated. It's just a kind of 2 kind of weights, basically. And the question is that you have a graph, you have S and T, and if you just ask if there exists a ST path P such that the weight is less than some threshold, then this is just shortest path. But now the question is just, you would like to find a path such that simultaneously